Hi all. So Dr. Stuart is going to join us in maybe 10 minutes or so. So as of now, just we will just wait for the attendees to join. Thank you. Okay, hi all. Dr. Stuart has already joined in. So I will ask him to turn on the video and audio, and then we can start with the session.
Hello, Samir. Can you hear me now?
Yes, I am able to hear you. How are you?
I'm very well, thank you. It's so lovely to be here and so wonderful to see you. It's a very big pleasure for me.
Yeah, yeah, sure. So, okay, let's start with the session. So I will just quickly introduce Dr. Stuart Clark and tell a bit about Asteroid Day, and then we can just switch over to Dr. Stuart Clark and listen to him. So just give me a minute. I'm sharing my screen. So I hope you guys are able to see my screen. Just give me a minute. Okay, so let's start with the session. So, just give me a minute. Okay, so this particular event, Asteroid Day, June 30th, is celebrated as an International Asteroid Day, and it's celebrated every year. Last year also, we have participated in this Asteroid Day, 30th June, and in fact, we won third prize from Asteroid Day internationally. So why it is celebrated, I will just give you a quick background, and then we will be over to the panelists and the guests. Astro Day is a dynamic awareness and educational program to inspire the world about asteroids, their role in the formation of our solar system, how we can use their resources, how asteroids can pave the way to future exploration, and finally, how we can protect our planet from asteroid impacts. So, you guys must have heard a lot this asteroid or that asteroid is coming very near to the Earth. So, that is why Asteroid Day is celebrated over here. Asteroid Day events are held on 30th June each year to mark the anniversary of the 1908 Tungska impact. Asteroid Day is a program run by Asteroid Day Foundation, which is a not-for-profit based out of Luxembourg. So I will just, I won't waste time. I will quickly introduce Dr. Stuart. Just give me a minute. I'm waiting for one more participant. Just one minute. Okay, Adarsh is not joining, I think. Okay, I will just introduce him quickly. So our guest is Dr. Stuart Clark. He's an astrophysicist. He is a widely read astronomy journalist. His career is devoted to presenting the complex world of astronomy to the general public. Dr. Stewart holds a first class honors degree and a PhD in astrophysics. He is a fellow of the Royal Astronomical Society and a former vice chair of the Association of British Science Writers. On 9th of August 2000, UK daily newspaper The Independent placed him alongside Stephen Hawking and the Astronomer Royal Professor Sir Martin Rees as one of the stars of British astrophysics teaching. Over the years, he has written many journals, articles, and books for BBC Sky and Night, BBC Focus, The Times, The Guardian, and so on. So he has written text for an issue of stamps for the Royal Mail. He writes an online blog for The Guardian called Across the Universe, read around the world. So these are the snapshots what I have taken from Amazon. I have read The Unknown Universe, 10 chapters, and Sky's Dark Labyrinth. So I whenever I get time, I go through his YouTube channel, the videos, whatever has been shared, even though they are old ones. So welcome, Dr. Stuart.
Thank you, Samir. It's really a big, big pleasure to be here with you. I'm
Yeah, it's
very
an honor.
pleased to be able to help.
Yeah. So just give me 2 minutes. I will just introduce my panelists, my team.
Please do.
Okay. So today's panelists are myself. I am founder of Spaceport India, which is a private not-for-profit organization. I am amateur astronomer and rocketer, and by profession, I'm an IT project manager. Naveen NS, he is a science communicator, amateur astronomer, and aero modeler. Karthik, he is a science communicator, amateur astronomer, and aero modeler. Cavalier Reddy, she is our solar system ambassador, the first one, and our team member. Sivapriyan, he is again a solar system ambassador and our team member. Plus, he has discovered two provisional asteroids recently, last month, and during our asteroid search event. Adarsh Sajan is going to join us soon. He is also a solar system ambassador. So I won't waste time on this one. So we will just start with Dr. Stuart presenting his screen. So please, Dr. Stuart, you can continue.
Well, thank you. I thought what I would do is just start with a small chat about asteroids and what they are, why we're interested in them, and then we'd use most of our time today to answer all the questions that you have sent along and want
Mhm.
answers to. Because I have to say, the breadth of the questions was so interesting to me as I was
Mhm.
reading through them today. And there was a couple of really difficult questions that I'm glad that you'd sent through to me before, so I could have a chance to do a bit more research and look up some answers. And some of them, I'll tell you which ones they were when we get there. They
Mhm.
surprised me as well, and gives me new things to think about.
Oh, that's really wonderful. I don't think you won't be able to answer anything, or you had to do that much of research work, I guess so.
Yeah, I had a. There's. Well, I'll tell you the ones that really that really made me think later on. So the asteroids themselves, there's millions of them, and it's a particularly important time now for us to be thinking about asteroids, because as astronomers we always work at the very cutting edge. We work at the things we can only just see and just detect. And now is the time when the telescopes are becoming big enough and the cameras are becoming sensitive enough that we can really start seeing just how many asteroids there are in the solar system. And we now have spacecraft that are capable of visiting these asteroids. And every time we go to an asteroid, we see that it's an individual, that it's completely different from other asteroids that we go to. This is an extraordinary population of solar system objects. They each have their own chemical compositions. They each have their own stories to tell us about how the solar system formed, because the asteroids themselves are the remnants, if you like, of the formation of the planets. They're the bits of rock and metal in the solar system that, for various different reasons, didn't become a planet itself, but they're so they're the remains, the leftovers from the formation of our 8 planets in our solar system. And this means that they have stories to tell us about that time, 4.5 billion years ago, when the solar system was forming. So some of the asteroids that we see contain mostly rock and silicate material. Other asteroids that we see have more metals in them. There's one particular asteroid called Psyche that we think may be a completely metal asteroid. And this is particularly interesting because when we make planets, they form because objects like asteroids collide together, and they sort of collide by traveling in the same direction and just nudging into one another quite gently. If they collided head on, the energy that they would release would shatter them and break them to pieces. But if they collide more gently, a more sort of low energy sort of impact going in the same direction, then the energy can simply melt them and they coalesce and form together. And when they melt, the densest material sinks to the very center of this new larger asteroid. And so that's where the metals come from. All the metals then sink into the center to form a metallic core. And we think there are metallic cores in all of the planets. So to find an asteroid, Psyche, which seems to be mostly, if not all, metal, that would indicate that it was once at the center, in the core of one of these larger asteroids, perhaps even a small planet on its own, and that it was subsequently shattered and broken back into fragments. So some of the asteroids, we think, some of the larger ones perhaps, are the leftover remnants of the formation of the planets. Many of the smaller ones, however, are ones that have been shattered from larger asteroids themselves. And piecing together this story of the asteroids, how they formed and how they're continuing to evolve today, is telling us a huge amount about how our solar system formed, how our planets formed, and how it continues to interact today. Now, although most of the asteroids are found in the asteroid belt between Mars and Jupiter, there are some families of asteroids and individual asteroids that cross the orbits of the inner planets, and these we tend to call the near-Earth objects or the near-Earth asteroids. And so some of those, if they travel past our world, they have the potential to strike us and to impact. This is a very, very rare event. In the course of our individual lives, the chances of an asteroid actually hitting us are very small indeed. A large asteroid hitting us are very small indeed. But over geological time, the probability becomes higher until, when we're talking about millions of years, then it's an absolute certainty. As many of you, I'm sure, know, it's now widely thought that the extinction of the dinosaurs was caused by the impact of a very large asteroid, perhaps a kilometre or so in size, maybe larger. So we have a duty as astronomers to look for asteroids and to try to detect as many of them as we possibly can, and to track them and to calculate their orbits to see if there is any that will cross Earth or could potentially be hazardous to the Earth in the future. And once we identify which of these asteroids could potentially strike the planet, then we can begin to work in ways of deflecting these asteroids, just giving them tiny, tiny pushes so that they cross the Earth's orbit half an hour, say, after our planet has passed through that region of space, and then we're perfectly safe. Now, the asteroids themselves will congregate anywhere that there's a sort of a gravitational space for them. And so a lot of the asteroids are between Mars and Jupiter, because this is where the gravity of Jupiter sort of keeps them, it shepherds them in this place. You'll find other asteroids in the orbit of Jupiter itself, before and after the planet. These are the Trojan asteroids. There's even a small band of these Trojan asteroids with some of the other planets as well, actually in the orbit of the planet. And then as we move into the outer solar system as well, we get to the Kuiper belt, and this is where the icy asteroids can be found. So the future of our study of the solar system will largely be based around asteroids because we're getting better at seeing them and detecting them, and we're also getting better at analyzing the asteroids. At the moment, there are two missions, one from Japan called Hayabusa 2 and one from America called OSIRIS-REx. And both of these missions aim to bring asteroid samples back to Earth, so bits of rock taken from the surface of these asteroids. And once we can get these back on Earth, then we can analyze the composition of these two asteroids with our laboratories here on the ground. And the equipment and the analysis and techniques that we can use is much more precise than can be flown into space on even the most advanced of the spacecraft. The two asteroids that we're bringing samples back from, one is Yugu. This is the asteroid that Japan's Hayabusa 2 mission went to, and the other is asteroid Bennu, which the OSIRIS-REx mission is preparing to try and take samples from this year. Both of these asteroids are absolutely fascinating because they appear to be piles of rubble, really. They're not solid rocks in space, but they're conglomerations of bits of rubble from shattered asteroids. So probably they formed in the wake of an asteroid collision that shattered the original body into pieces. It's even possible that these two objects formed from the debris of the collision of the same parent asteroid. But what's fascinating about that is that they're both very different. Whereas Yugu is dry, Bennu has a lot of hydrated minerals, so there's a lot of water there on Bennu. And it's this kind of water that we look towards in the future, of extracting water from asteroids so that we can make oxygen out of the water for astronauts, and also hydrogen and oxygen, which can be used as rocket fuel from the asteroids. It's even possible that Bennu contains a lot of carbonaceous compounds, and there's a form of meteorite that rocks that fall to the Earth called the carbonaceous chondrites. And the carbonaceous chondrites come from asteroids, and they contain carbon molecules in many different forms. And as we know, carbon is the essential element that makes up the DNA in our cells, which gives us life. And so it's possible that the asteroids themselves brought some of the material that made the origin of life on Earth possible 4.6 billion years ago. So we may have 8 large planets in the solar system. We may have many dozen dwarf planets in the outer solar system, Pluto and Eris and some of these other worlds that are being discovered. But we have millions, many millions of asteroids out there, and all with stories to tell. So as we go into the future and we continue to study our solar system, the asteroids are going to play an increasingly important role in that, both in telling us about the formation of the solar system, about the formation of the Earth, perhaps even about the formation of life itself, but also in helping us to explore the solar system because of the resources, mineral, metallic, and more volatile like the water, those resources that we can find on the asteroid and that we could be able to use in future in our exploration of space. So this is why we have Asteroid Day, and it's as Samir said, it is a global day of asteroid education, and we've been running now for Oh gosh, let me think. It was 2014, I think, that I first got involved with the very first Asteroid Day here in London, and we had an event at the Science Museum in London, in which I talked to many of the scientists and the engineers that were working at that time on asteroids. And now it has grown into something that reaches across the world. And so it's with thanks to all of you for being interested and making Asteroid Day have this global reach. And I look forward to many more years of this education and this coming together as a global community, regardless of what country we live in, to work in the service of knowledge and understanding. So thank you very much again for inviting me here, and we can go to the question and answer session.
Sure, sure. So before just starting the Q&A, I am, in fact, I keep on receiving this question all the time. Why, how space rocks are different from the Earth rocks? Even our Earth is in space, right? So if suppose I'm an alien or I am extraterrestrial living on some other planet and Earth rocks come to me, for obviously for me it's just a space rock, right? So can you just help us or kids understand what is the difference between space rock and the Earth rock? Then maybe we can start with the Q&A.
Certainly. It's a really good question. So essentially, yes, the Earth and the rocks on the Earth, they're made of exactly the same material that is made, that the asteroids are made from. On the Earth, however, we have many dynamic processes. So the interior of the Earth is still largely molten, and so the rocks that we have on the surface, very few of them are the same as when they originally formed 4.5 billion years ago at the beginning of the solar system. Even the rocks that are there and are very old, billions of years old, they have still been subjected to weathering and chemical alteration by the atmosphere and by rain and all the other processes that go on in the atmosphere. They've also been altered by life itself. So when we find meteorites on the Earth, we can analyze them and we can find some of these organic compounds in there that are the building blocks of life itself. But we don't know for sure whether those building blocks of life were present in the formation of the solar system, or whether this is contamination in the rocks since they've fallen to Earth. So out in space, where the asteroids are, many of them have remained completely unchanged since the origin of the solar system, 4.5 billion years ago, and so they're like a time capsule. We can look at the rocks from these primitive asteroids and then compare them with the rocks on the Earth, and often those differences will be in the minerals that we find in them. And to a geologist, that can tell them about all the processes that have happened both in the early solar system and today on Earth, and everything that's happened in between. So that's why the asteroids and the space rocks are so important to us.
Okay, thank you. Yeah, so I will just move on to my co-host Naveen so that he can ask you more questions about it.
Good evening, sir. Nice
Hi
to meet
Naveen,
you.
how are you?
Yeah, good, sir. Very fine. What about you, sir?
I'm very well, yes, I'm very well.
Thank you, sir. Thank you. Thank you. Sir, actually, do the asteroids become hurdles to the interplanetary missions, sir, in future?
Yeah, this question. Uh, it took me back to my childhood actually, because before spacecraft had gone to the outer planets, Jupiter and Saturn, Uranus and Neptune, no one really knew whether the asteroid belt itself was dense with asteroids, or they were very widely far apart. And in fact, as a child, I would watch films like Star Wars, going through asteroid fields, and I would think that that was how dense the asteroid belt was. And some of the engineers at NASA, when they originally sent these missions out, they thought there was a possibility that they wouldn't make it through the asteroid belt itself, that there would just be so many more space rocks there that we couldn't see with the telescopes of the time. Well, now we know that whilst there is still a hazard always that we will collide with a space rock that we didn't know about, a small one, there's large parts of the asteroid belt that are essentially empty. That so we can quite safely navigate through the asteroid belt and get to the outer solar system. Interestingly enough, however, is when you come down to the size of dust grains. So imagine that Ceres is the largest asteroid with a diameter of about 1,000 kilometers. Well, you can come all the way down in size to little grains of dust about a millionth of a meter across. And as you come down in size, the smaller you get, the more objects that there are. And when you get to the size of dust grains, then our spacecraft are constantly being hit by these dust grains, these micrometeoroids, as we call them. But our spacecraft are robust enough that they can survive this.
Thank you, sir. Thank you. It's a very nice explanation, sir. Then one more question, sir. Is there a possibility that life in the air is not created in the air? It came from the asteroids, because asteroids carrying the organic molecules, as you said earlier. So
yes, this is one of the biggest mysteries in science. And it is one of the questions that I would really be interested in seeing answered. And that is, how did life begin? Because there's definitely, when we think, the chemical precursors of life, the sort of building blocks of life, the kind of organic molecules, particularly things called amino acids, which make up all of our proteins. Well, we think we find those in meteorites, and therefore we should find them on asteroids as well. So it seems to me very likely that asteroids could indeed have brought, at the very least, those building blocks of life to the Earth, and that some kind of process, whether it was at the deep ocean floor or in a warm geothermal pool on the surface, that in those kind of watery environments, that the chemistry took place that then became biology and life. But there's also the possibility that the life itself could have been brought here, maybe from another solar system or from another planet. Perhaps the origin of life took place on Mars, and it was meteorites from Mars being exploded into space by the impact of asteroids there that brought the life to Earth. At the moment, we simply don't know, and this is why we need to continue to focus our research on trying to understand exactly how life formed, and once we know how it can form, then we can look at the most likely place for those conditions to be met.
Thank you, sir. Thank you.
You're welcome.
Thank you. Thank
you. So next set of question is from Karthik.
Hello, sir.
Hello, Karthik. How are you?
Yeah, I'm fine, sir. Great, sir.
It's good to see you. Yep, I'm very happy.
Thank you. So my question is, can we calculate the age of asteroids with the help of radiocarbon dating, sir?
Yes, this is a fascinating question as well. So we do use radioactive dating or radioisotope dating, but carbon doesn't work for us because it can't get the timescale back long enough. So with carbon dating, or I should say with radioisotope dating, What we are looking for is the radioactive decay of those elements. And there's a concept called half-life in radioactive decay, and that means if you have a kilogram of a radioactive substance, then half of it will have decayed into another element in the half-life. So in the case of carbon, carbon's half-life is about 5,000 years. And so you can only reliably date to around about 10 half-lives. After about 10 half-lives, there's too little of the original isotope left for you to be certain about your dating. And so with radioactive carbon, carbon-14, you can only date to around about 50,000 years ago. Now, the asteroids, we think, are about 4.6 billion years old, so billion, not thousands or millions. And for that, we need to use isotopes of uranium, because they have half-lives that are measured in billions of years. And so we can look at the meteorites and rocks that we are now getting from the asteroids, and we can start doing this radioactive dating, first having a look at the carbon to get us back a little way, then having a look at some of the other radio elements, in particular in particular uranium, and that will then give us these more precise ages for the asteroids. So yeah, that's how we do it.
Okay. Then I have another question. How can we determine the mass of a rock in space without gravity? So actually in Earth we are using acceleration due to gravity value something. In space, what we do?
Yes. So this is fascinating, because the asteroid itself generates a gravitational field, and the gravitational field that the asteroid generates is determined by its mass. So when you have a spacecraft fly by an asteroid, or go into orbit around an asteroid, then Newton's law of gravity, his famous equation, which says that F equals gmm over r squared, you can use that to measure the mass of the asteroid, because the spacecraft feels the force of gravity from the asteroid. So that's the F in that equation. You know the mass of your spacecraft, so that's one of the M's. R, the radius between the spacecraft and the asteroid, you can calculate with a laser altimeter on the spacecraft or some other kind of navigation. And that means that the only variable in that equation that you don't now know is the mass of the asteroid. G itself is a constant of nature, so we measure that in earthly laboratories. So you can just rearrange that equation and solve it to get the mass of the asteroid. So that's how we do it effectively, is we look for something that's in orbit around an asteroid, either a spacecraft or a moon, another little asteroid. Then we can measure precisely.
Thank you, sir. Sir, one more last question. Is the orbital mechanics of rocks and asteroids and planets are equal, sir?
Yes, the asteroids, the meteors, and the planets themselves, they all follow, and the spacecraft we put there, they all follow Newton's laws of motion and his law of universal gravitation. And I find this super fascinating. I mean, it's 25 miles up the road from where I'm sitting right now is Cambridge. And in 1687, that's where Isaac Newton calculated all of the maths that we still use today to calculate the orbits of the planets and the orbits of the asteroids and the orbits of spacecraft. If we could somehow bring Newton back to life and sit him down here in the panel today, he would understand exactly how we calculate these orbits. It's nothing new to him. because he did it for comets originally. He did it for the planets originally and the comets, and then Edmund Halley, another English astronomer, he did it for Halley's comet as well. And that's how we do these calculations today. Now, when it comes to asteroids, there is a slight difference to planets, and that is that the asteroids themselves are small enough that they're not completely ruled by gravity. So some other effects can slightly influence their orbits. And one of those effects is something called the Yarkovsky effect. And the Yarkovsky effect is what happens when you have an asteroid in space and it's rotating and the sun is heating it from one direction. So as the asteroid rotates, it heats up this side of the asteroid, and then that asteroid rotates and it moves the hot side of the asteroid away from the sun and onto the nighttime side. And then the infrared radiation from the heat of the asteroid, it radiates back into space, and that gives the asteroid a little push. So asteroid orbits evolve because they often have this little push if they're close to the sun from the Yarkovsky effect. So whereas planets mostly stay completely fixed in their orbits, the asteroids move a little bit. Their orbits evolve and change slowly with time, and this is why it's increasingly important for us to continue to continuously track them so we can always know where they're going.
Thank you for wonderful answers, sir.
Thank you.
Sivapriyan, sorry, I was on mute. So you can ask the questions.
Good evening, sir.
Hello, how are you?
Fine, sir. What about you?
Yeah, I'm really good. It's it's a typical English summer here in that it's really quite cold today. So, but at least it's not raining.
Okay, sir. So, can we use asteroids as a safety barrier against any extraterrestrial attack?
This absolutely fascinates me. So, tell me a little bit more about what you think we might be able to do. What kind of things are you thinking of?
So, how mining of the asteroids will help?
Sivapriyan, sorry, on the first question, he is asking you something.
Sorry, sir.
Yes, in order for me to correctly answer your question, tell me a little bit more about how you think we might be able to use the asteroids and what sort of attacks you're thinking of, like we see in the movies.
Yes.
Yes, sir. It's alien attacks.
So the first thing to say is that we still don't know whether there's anything like extraterrestrial life or aliens that are out there. And I suppose if you, I think it would be very difficult to use asteroids to try and repel an alien invasion force, because I think they're going to have much more technology than we have. Now, if you're interested in these kinds of things and they're subjects that science fiction books and films are really good at exploring, I'm just watching a television series at the moment which I think you would really enjoy, and it's a television series which is called The Expanse. And a lot of The Expanse is set in the asteroid belt, with asteroid miners, and looks at the colonization of the solar system and what might happen if we were to ever detect evidence of extraterrestrial life.
Okay.
Okay, sir. How mining of asteroids will help considering the fact that cost of mission might be high?
Yeah, you see, you've asked absolutely the key question there, because at the moment, the cost of sending missions to these asteroids is very high. And the idea of sort of going to an asteroid and mining it for, say, the precious metal like platinum and bringing that down to Earth to use on Earth, it's just too expensive to do, really. And so the idea of using all those minerals and resources that are on the asteroids down here on Earth is a very long way away. But the one thing that the asteroids do have, which may be of extreme interest and importance to us as we explore the rest of the solar system, is water. So I mentioned this a little bit in my introduction, but it's well worth expanding upon here. Because once you find water on the asteroids, and asteroid Bennu looks as if it has clay minerals on there, so that's clearly a sign of water and hydration. If we can extract that water, and then we can break the water, which is H2O, we can break that water molecule into hydrogen and oxygen, then hydrogen and oxygen are the rocket fuels that power most upper stages of rocket engines. And in space are loads of upper stages of rocket engines which have been used to put other satellites and spacecraft up there. So they're just sitting there at the moment as space debris. But if we could catch them, tow them to an asteroid, we could refuel them with the hydrogen and the oxygen that we would find on the asteroid, and then we could use them to launch other spacecraft further into the solar system. And so in the future, the first thing I think that we will see the resources on the asteroid used for is for space exploration, how to get further and do other missions. And then gradually, as we extend our presence into space, so I think we'll start to use the resources on the asteroids, such as other minerals or metals, in order to build more things in space, such as bases, maybe even lunar or Mars bases.
Okay. So we have Cavalier ready. So she will ask the next set of questions.
Good evening, sir.
Hello, how are you?
Fine, sir. How are you, sir?
Yes, very good. Very happy to be talking to you all.
Thank you, sir. My question is, why are there more asteroids in Kuiper Belt and near Jupiter?
So when you say more asteroids there, do you mean more than in the asteroid belt, or do you just mean why do we find asteroids beyond the asteroid belt?
More in asteroid, right? More in asteroid belt.
Yes. So the solar system, when it was formed, there was billions upon billions of asteroids. And in the context of the formation of the planets, we generally refer to them as planetesimals. That sort of just means small, tiny planets. But they're no different really from the asteroids. And as the planets came together and these planetesimals, these asteroids, collided and formed into bigger objects, some of them had near misses. They didn't hit each other, but they had just close passes. And if they did that with larger and larger planets as they got to form, so the small asteroid going past had a gravitational interaction that threw it out into the outer solar system. And these kinds of gravitational interactions are the things that we use with spacecraft today. The slingshot effect, where we use a close gravitational pass to give our spacecraft extra energy. Now, when that happened to many, I mean, possibly millions and millions, or even a billion or so of these asteroids, they got thrown into the outer solar system. And many of them now are way beyond the planets, in the Kuiper Belt, as you say, and out into the even larger area called the Oort cloud. And many of these are very icy as well. And so when they fall back into the solar system, they become the comets that we see.
Thank you, sir. And another question is, do you think with the uses of AI technology, we can protect the Earth from fast-moving asteroids?
Yes, artificial intelligence and AI technology have a leading role to play. And where they will become most important soonest is in the detection of asteroids. So there are a number of telescopes and observatories that will soon be coming online. One in particular is called the Vrc Reuben Observatory, and this telescope will discover thousands upon thousands, tens of thousands of asteroids. I mean, already we have surveys that are discovering 5 to 10 asteroids a night now. And as this increases, what we're going to need are artificially intelligent computer programs to look at the data and to find those asteroids for us, and then to keep track of those asteroids and to compute their orbits. There's a project called Project Atom, and this is a project that's been started by the NASA astronaut Ed Lu through his B612 Foundation. And Project Atom will create open source cloud computing software routines that will detect asteroids from data and compute their orbits. So this is absolutely the future of finding asteroids. And if we need to deflect asteroids, then we probably need to hit the asteroid with something to give it a nudge and move it out of the way. And there's going to be a test next year, in fact, of this technology. NASA is launching its DART mission. It stands for Double Asteroid Redirection Test. And DART will close on its asteroid. It'll approach its asteroid very, very quickly. And onboard DART will be what are essentially artificially intelligent software routines that will be guiding the spacecraft to its target to make sure it hits this little asteroid dead center and just changes its orbit by a very, very small amount, but enough for us to measure and know that we can do it.
Okay, thank you.
Thank you, sir.
So next is our panelist Adarsh. He's going to ask some questions.
Good evening, sir.
Hello, Adesh.
How are you, sir?
I am very well, thank you. You look as if you've got some really cool space rocks behind you.
Yes.
Yes, sir.
He made that model and it lights up also.
Fantastic. That's
Thank you, sir.
wonderful.
Thank you, sir. Sir, I have two questions to ask. My first question is, how comets' exact location and speed are calculated?
So that's a good question. And what we do is we take pictures of them night after night, and then we look to see how they have moved in relation to the background stars. So the background stars in the night sky are like fixed location points for us. And by triangulating the movement of the comet across that backdrop, that fixed backdrop of stars, we can calculate the orbit that it's moving on and how fast it's going.
Thank you, sir. I have one more question to ask. Do all space rocks contain minerals in them? What kind of minerals are seen in space rocks?
Yes, all of the space rocks have minerals. So the minerals themselves, they're chemical compounds that form naturally inside all rocks. And many of the minerals that are found in space rocks are very familiar to us on Earth. So they're minerals such as pyroxene and olivine, so things that geologists study all the time on the Earth, and that speaks to us that the asteroids and the Earth and the other planets have this common origin.
Thank you, sir.
Thanks. So, Dr. Stewart, we have around 4 more questions out of the pre-listed ones, plus I think 30 more questions. So, would you like to take a break, or how should we proceed? Or should I shoot out the questions?
Shoot out the questions. I'll try to be. I love the subject so much that I tend to talk an awful lot about it. So I'll try to keep my answers a bit shorter.
And I just wanted to tell you, I have this small collection of meteoroids. They have been actually already chemical analysis been done. Most of them are carbonaceous only, LL5 and 6. So maybe I will discuss this further in our next subsequent webinars. So just moving on to the questions. Are asteroid species of rocks broken apart from the bodies in our solar system, or are they extraterrestrial origin?
Mostly they have come from planets, or they've come from our solar system. So they are the remains of a planet which never really formed. It looks as if there could have been another planet between Mars and Jupiter, but the extremely strong gravitational field of Jupiter sort of kept the asteroids in orbit and corralled them into orbit. And stopped them coming together. So the vast majority of asteroids, we think, come from the solar system and were formed at the same time as the planets. But there are some objects in our solar system that could be captured from beyond. And we definitely have seen 2 extraterrestrial or extrasolar asteroids, come through the solar system. Oumuamua, a few years ago, was the most famous example of that. When we computed its orbit, we saw quite clearly that it was coming from outside of the solar system, and that it wouldn't be captured by the sun. It would just be mildly deflected by it, and so head off into interstellar space again. And we expect that the Reuben Observatory and other surveys may probably find 1 or 2 such interstellar asteroids every year once those studies start to come online.
Yes, right. So, thank you. So the next question is, can we measure the electric potential of an asteroid belt, or rather asteroids?
Yeah, this was the question that you sent me earlier that had me really thinking. And in fact, I found a paper from about 3 years ago that has something very, very interesting to say about this. So I talked a little bit about Rubble pile asteroids. I mentioned them in passing. This idea that not all the asteroids that are out there are single sort of slabs of rock, what they call monolithic asteroids, but instead they're aggregates of fragments from other shattered asteroids. And there is some work that was done that suggested that these rubble pile asteroids, these aggregates, the electrical forces between them, the electrostatic forces between the individual rocks, and these these electrical bonds called van der Waals forces, that they hold or help hold the asteroids together. So it appears as if there is electrostatics to be measured at the asteroids, and that also they play a role in making the asteroids what they are today. So I learnt something by preparing for our webinar today.
Okay, that's good to hear. Okay, next question is there a possibility that the Earth will end due to an asteroid hit? How can we deviate it from hitting the Earth?
Yes, so is a remote possibility in our lifetimes that we're going to be hit by an asteroid capable of doing real damage. And we're already working on detecting those if they exist, and also working to work out how we can deflect them. So the NASA mission DART, as I was talking about, that will hit the small asteroid Didymos B head on and try to change its orbit by a very, very small amount, so that we can be sure that we can hit asteroids, we can actually target them and hit them, that we can change their orbits, and that we can, once we survey and understand the asteroid, then we know exactly how to do it for other, perhaps even larger objects in the future. So this is something that's ongoing, and that a lot of the space agencies around the world are working on.
Right, correct. So the next question is, do we know anything about the magnetism or the magnetic field of asteroids?
Yeah, we know. So there's a group of meteorites called the Pallasites, and these show a lot of the influence of magnetism in them. So we do not expect the asteroids today to have strong magnetic fields. There might be some sort of weak, local, very localized magnetic fields, a bit like there are on Mars. Mars itself does not have a large magnetic field like the Earth does, but it has small localized areas of magnetism. And we expect the asteroids to be the same as this. And the reason is that the magnetic fields, large-scale magnetic fields, like we have here on Earth, that's generated by having a molten core. And the molten metal core is moving, and that generates the magnetic field. Now, when the asteroids were first formed billions of years ago, and perhaps persisting for tens of millions of years while their cores were still molten and solidifying, then we see from the Pallasites, for example, that there were magnetic fields generated on the asteroids, and that the magnetic minerals in these meteorites and in these asteroids will be naturally lined up as they solidify and become rocks. So the asteroids have had magnetic fields in the past. If we go there today, we could measure any residual small-scale fields that are there, but we don't expect any of them to have large-scale magnetism like the Earth does.
Okay, yeah. So I will just take up some YouTube sessions, because we are streaming live on YouTube also. Is it possible that some of the asteroids get attracted towards Jupiter because of its higher attraction from the asteroid belt? So
yeah, Jupiter is the largest planet. It has the strongest gravity, and it does a very effective job of trapping asteroids in its gravitational field. So there are, in the asteroid belt itself, there are things called Kirkwood Gaps. And the Kirkwood Gaps are areas of relatively few asteroids, and those asteroids have been kicked out of the way by Jupiter's gravity. And the asteroid families that remain around the gaps are held there by Jupiter's gravity. It's exactly the same as the moons of Saturn due to Saturn's rings. The rings there have gaps in them, and that's because of the gravity of the moons of Saturn holding the pebbles and the rocks in the rings, and Jupiter does that with the asteroids in the asteroid belt.
Okay, okay, lovely. So next question from YouTube is, does dark matter controls asteroids? I think this one is interesting.
Yeah, so we don't think that dark matter controls the gravitational field of the solar system, because when we use Newton's laws, we just see the gravity coming is overwhelmingly coming from the planets and the sun, and that's what's moving the asteroids. So the dark matter that gets talked about is only significant on extremely large volumes, things that become cosmologically important, and where there is no other or no large reserves of normal matter.
Right, right. So next one, what is the safest distance our Earth should be with respect to asteroid passing by? Basically, it's near Earth object orbits. So, what should be the safest distance of the Earth?
Yeah, any distance, so long as it doesn't enter our atmosphere, is actually safe. So you sometimes hear about asteroids that are coming so close to the Earth. There's at least one I can think of that passed in between the geostationary orbits at 36,000 kilometers in altitude and the Earth. And there's an asteroid that came sort of close in between those in that ring. Other times you hear about asteroids passing within the distance of the Moon from the Earth. Because space is frictionless, it can pass as close as it likes, and it won't suddenly fall into Earth or be deflected. It's only if it touches our atmosphere that it starts to slow down, and then it may slow down enough that the gravity of the Earth pulls it down. So anything above the atmosphere, and remember the atmosphere itself is pretty much gone by, let's say 500 kilometers. You're in deep space really there. Well, that's fine.
Okay, so we have 35 more questions to go. I don't know. Okay.
My answers will become shorter.
Yeah, that's correct. So someone has asked, please tell us about asteroid Bennu in detail a bit more. Why we have selected this particular asteroid?
We selected it because from the Earth it looked as if it had this really interesting composition. We could see there looked as if there was evidence of water and clay minerals and carbonaceous compounds on the asteroid. And now that OSIRIS-REx has got there and started this really in-depth look at the asteroid, we're not disappointed in any way. It's an absolutely fascinating mission. So to find out more about it, Google asteroid Bennu or go to the OSIRIS-REx website at NASA.
Yes, yes. There is one question, why Ceres is considered as both as an asteroid and a dwarf planet? How is it possible? How big does an asteroid need to be called as a dwarf planet? So what is the difference or definition of dwarf planet and an asteroid?
So anything that's roughly spherical in shape is what you would consider to be a dwarf planet. And Ceres was the first asteroid to be discovered in 1801, and so it's an asteroid for that reason. but by the definition that the International Astronomical Union determined for dwarf planet, which is anything sort of about 1,000 kilometers in diameter, which is thus a spherical body. Ceres can also be considered as a dwarf planet as well.
Okay. So there was just one related question over here. Why asteroids are not spherical in shape?
Yes, that's because the gravitational fields generated by the asteroids is not strong enough to overwhelm the strength of the rock. So we know on Earth, if we pick a rock up, we can't mold it into shape. If, however, you get enough rock together and you have about 1,000 kilometers in diameter worth of rock, then the gravitational field that will generate is strong enough to actually deform the rock, and that will pull it into a spherical shape, which is a very stable gravitational shape.
Okay. So, sure. The next question is, can we calculate the age of an asteroid using uranium dating?
Yes, that's exactly how we do it. Yeah.
Okay. Uh, okay. One question is more related to career guidance. What studies or what further study should be done by a 12th class grader take up it as they are interested in physics, astrophysics, astronomy, cosmology, who wants to work with NASA or as an astronaut?
Fantastic. So, if you want to go into the actual science of the subject, as it were, you have to decide whether you want to be, say, a planetary scientist or whether you want to be an astronomer, astrophysicist. So, if you want to be an astrophysicist, then it's physics, it's maths. You'll be looking at what makes up the celestial objects, how they work, those kinds of things. If you want to become, you can also become a sort of more of an observational astronomer, so working at the telescopes and taking the data. Then again, it really is physics and maths, but it's also having an interest in the engineering and how you make the hardware itself. And there's also the route of being a planetary scientist, so that's more geology, that's less physics, less maths, and more geology and chemistry. So there are a number of different routes to there. In terms of becoming an astronaut, then for the generation of people growing up today, there will be more and more opportunities to actually do that. And there, I think the best training is sort of being physically fit and able.
Okay, sure. So I will take up just maybe three more questions. Why asteroid, whenever we look at the images of asteroids, why are they more grayish color rather than very colorful picture, just like on Earth, blue, green, minerals and all. So why they are gray in color?
Yeah, they are. They're not very colourful, are they? They're just boring rocks in space. In fact, to get them to be that grey colour that you see in images, and some of those images are black and white images, but to get them to be that sort of colour, you have to enhance them quite a lot because most asteroids are as black as coal. It's incredible that they're that. This is because of the way that the sunlight has reacted with the chemicals on the surface. So, unfortunately, yeah, asteroids are not very colourful places.
Sure. So next question is, which many kids have asked me earlier also, when asteroids are moving in between Mars and Jupiter or beyond Jupiter or beyond Neptune, how come they are all of a sudden coming towards Earth, where the probability is high that they may or may not hit the Earth? So when does this happen?
So everything that's in orbit in our solar system is in orbit around the sun. So everything has the potential to sort of fall inwards towards the sun. The objects that come close to the Earth and do this, they've been perturbed in some way. They've had some orbital energy taken from them, if you like, or they've been put in these very large elliptical orbits that do take them out a very long way. But eventually they will fall back into the inner solar system and come back in the vicinity of the sun and the Earth. So it's simply sort of an accident, really, of orbital dynamics. The comets that tend to fall in from even further, they've probably been destabilized in their orbit by a passing star or something. And that star may have passed us millions of years ago, and it's taken that long for these objects to fall in from the very, very furthest reaches of the solar system.
Okay, right, sure. So someone asked just now, this is the last question from my side. Whatever is there, maybe I will shoot up these questions to you via email. What is your last or the latest current research work going on? If you can tell us a bit more, what research work, how kids can also get involved, or how they can learn further in astrophysics.
Yes, so there are a number of online citizen science projects, as they're called, and this tends to be using home computers in order to analyze astrophysical data. If you have access to an observatory as well, there are a number of things that you can do in the search for asteroids, as you know. So places to look for these kinds of things are the websites that deal with Galaxy Zoo. So Galaxy Zoo is a way that people can help classify the galaxies that are being found in these large surveys. Also the Planetary Society, that also will have ideas about how you can contribute to finding asteroids. And there's even grants available for amateur astronomers who want to use their observatories to help find asteroids. So the other way to stay current with what's going on in astrophysics are to read the websites like space.com, newscientist.com, and newspapers, and see all the things that are happening. It's all there on the web, and I encourage everybody to go and have a look, because it's very rewarding.
Sure. Well, that's it from our side. There are more questions shooting up. Maybe we will need to have another session, or I will just send out via email. So thanks a lot, Dr. Stuart. It was really nice and wonderful session. Everyone has given a lot of appreciation for this session, and they have learned a lot. So thanks a lot. And I really wish you very best of luck for whatever research work you do. And we would love to hear you on YouTube and via books and everything, whatever medium you use. So thanks a lot, and have a nice day ahead.
Thank you so much, Samir, for asking me, and thank you to all of you for asking your questions. It's been a real pleasure for me to connect like this with you. I'm overwhelmed by the support and all the questions and the chat and everything that's been going on. Let's do it again next year for Asteroid Day, or perhaps even sooner.
Sure, for sure.
Thank you, sir.
Thank you
so much.
Thank you.
Bye, everyone.
Thank you, sir.
Thank you all. So I'm just stopping the session.